Hey everyone, and welcome to this explainer. Okay, let's dive right into this. When you first look at a screen full of variables, exponents, and numbers all strung together, it's incredibly easy to feel a sense of abstract intimidation. But today, we're going to completely change how you see polynomials. Instead of viewing them as this chaotic jumble of math, I want you to look at them as a highly satisfying logical matching game. Because once you know the rules of how the pieces fit together, everything falls perfectly into place. So here's our roadmap for climbing the ladder of complexity today. We've got adding and subtracting polynomials, distributing the negative sign, multiplying binomials and trinomials, dividing by factoring, and finally, long division versus synthetic division. Let's get to it. All right, part one, adding and subtracting polynomials. This is the very first rung of our ladder, and if you can sort items into different buckets based on what they look like, you can absolutely do this. To do this sorting, you really just need one rule. Finding like terms. Basically, these are expressions that have the exact same variables and the exact same exponents. Think of it like this. X squared is a square peg and a plain X is a round hole. They just don't mix. You can only combine terms if they are literal twins in their variables and exponents. Simply put, combining like terms is the engine that drives the whole shebang of polynomial simplification. Let's look at this example. We're adding 4x squared plus 5x plus 7 and 3x squared minus 8x plus 12. Since it's just addition, we literally drop the parentheses and start filling our buckets. First up, 4x squared and 3x squared. Add them up, you get 7x squared. Next bucket, the x terms. We've got a positive 5x and a negative 8x. 5 minus 8 gives us negative 3, so that's negative 3x. And finally, the constants, just your regular old numbers. 7 plus 12 is 19. Bring it all down together, and our final answer is 7x squared minus 3x plus 19. Pretty satisfying, right? Moving right along to part two, distributing the negative sign. Now, as we transition into subtraction, I've got to sound the alarm. We're stepping into a classic mathematical trap here. Now, what's really interesting here is how one tiny little symbol changes absolutely everything. When you subtract a polynomial, that negative sign right in the middle applies to the entire second group of numbers. You must distribute that negative sign to every single term before you do anything else. If we subtract 5x squared minus 7x minus 14, that negative sign swoops in and flips the whole script. It becomes negative 5x squared, positive 7x, and positive 14. If you forget to flip those signs, well, actually scratch that. Let's just say you definitely won't get the correct answer of 4x squared plus 27. Always distribute the negative first. Okay, let's scale this concept up a bit. What happens if there are numbers in front of the parentheses? Well, first, on the left, we just distribute that positive 4. 4 times 3x squared is 12x squared, 4 times 6x is 24x, and 4 times negative 8 is negative 32. Easy enough. But now, for the really crucial part on the right side, we aren't just distributing a 3, we're distributing a negative 3. Negative 3 times 2x squared is negative 6x squared. Negative 3 times negative 5x, that flips to a positive 15x. And negative 3 times 7 is negative 21. Once you've got all of that distributed, you just combine your like terms again to elegantly arrive at 6x squared plus 39x minus 53. All right, rung 3, multiplying binomials and trinomials. We are definitely climbing higher now, and the sheer physical size of the equations we're about to tackle is going to expand. So when we multiply two binomials, expressions with two terms each, we use that trusty sequential method you probably remember called FOIL. First, outer, inner, last. Take 3x plus 5 multiplied by 2x minus 3. We do the first terms, 3x times 2x is 6x squared. Outer terms, 3x times negative 3 is negative 9x. Inner, 5 times 2x is 10x. And the last terms, 5 times negative 3 is negative 15. We generated 4 initial terms, but hey, look at the middle two. Negative 9x and positive 10x are like terms. We just combine them to shrink the whole thing down into a beautiful trinomial, 6x squared plus x minus 15. Now, I want you to hold this number in your head for a second. 6. If multiplying a binomial by a binomial gives us 4 initial terms, what on earth happens when we multiply a binomial, which has 2 terms, by a trinomial, which has 3? Well, 2 times 3 is 6. That means our calculation is going to explode into 6 individual terms before we can consolidate them. Which leads us to the narrative climax of multiplication, 9. No way around it. When you multiply a trinomial by a trinomial, 3 terms by 3 terms, you're going to generate a massive calculation with 9 separate terms. Setting up a grid like this is a total lifesaver for organizing the chaos of a problem this big. You take the top row, 2x squared, and multiply it down the first column. 2x squared times 3x squared is 6x to the fourth. 2x squared times negative 5x is negative 10x cubed. You systematically fill out all 9 cells this way, multiplying each term across. And here's the best part. Once your grid is full, your diagonal-like terms perfectly line up. You group the x fourths, the x cubes, the x squares, compressing this massive beast down to 6x to the fourth plus 8x cubed minus 28x squared plus 62x minus 28. Whew! Let's take a quick breather here. As our source material wisely points out, it's always good to double-check your work. Honestly, getting a 9-term polynomial right isn't a test of raw, innate genius. It's really just a test of patience, focus, and organization. Take your time, draw those distribution lines if it helps, and for sure, double-check that arithmetic. Moving into the home stretch with part 4, dividing by factoring. This is the most elegant method for simplifying polynomial fractions. Check this out. We want to divide x squared plus 7x plus 12 by x plus 3. Instead of some crazy long calculation, we can just factor the top trinomial. We're looking for two numbers that multiply to 12 and add up to 7. 3 and 4 hit the nail right on the head. 3 times 4 is 12, 3 plus 4 is 7. So, the top factors perfectly into x plus 3 times x plus 4. And since we are dividing by x plus 3, those identical terms cleanly cancel each other out, leaving us with a wonderfully simple answer, x plus 4. But, things don't always factor so neatly. So welcome to part 5, the grand finale, long division versus synthetic division. First up is the old reliable long division. It's a loop. Divide, multiply, subtract, bring down. Let's divide 2x squared minus 7x plus 6 by x minus 2. Divide the first terms. 2x squared divided by x gives us 2x. Then multiply 2x by our divisor, x minus 2, which gets us 2x squared minus 4x. Subtract that, and be super careful with your negative signs here, which gives us negative 3x. Bring down the positive 6, loop again. Negative 3x divided by x is negative 3. Multiply negative 3 by x minus 2 to get negative 3x plus 6. Subtract that from our remaining terms, and boom, the remainder is exactly 0. We land perfectly at a quotient of 2x minus 3. Now let's pivot to synthetic division for the exact same problem. Honestly, this is like taking the engine out of the car to make it sleeker and faster. Instead of writing all those variables, we just grab the coefficients of the numerator, 2, negative 7, and 6. And instead of dividing by x minus 2, we set that to 0 and just use a positive 2. The steps are super fast. Bring down the first number, which is 2. Multiply it by our divisor 2 to get 4. Add that to negative 7 to get negative 3. Multiply negative 3 by 2 to get negative 6. Add that to 6, and we get 0, our remainder. The numbers we have left are 2 and negative 3, which translates straight back into variables as 2x minus 3. And this brilliantly illustrates the real beauty of math. Look at these two completely different methods side by side. One uses the repetitive, traditional algorithm of long division. The other uses the sleek, coefficient-based speed of synthetic division. But math is this flexible, universal language. As long as you follow the rules, completely different paths will reliably guide you to the exact same truth, 2x minus 3. We've literally climbed all the way from basic like terms up to the heights of complex synthetic division. You now have a complete step-by-step toolkit for organizing, distributing, and calculating polynomial expressions. So here's my question for you. When you sit down with your next assignment, which mathematical path will you choose to conquer your next polynomial puzzle? Are you going to go with the methodical steps or the sleek shortcuts? The choice is entirely yours. Keep practicing, stay organized, and until next time, keep learning.